Hello friends, myself Dr. Nandakumar Raubavale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 1. This is our 26th lecture on Applied Thermodynamics 1. In previous lecture, we have discussed about numerical on reheat vapor power cycle where we have solved a problem on reheat cycle using steam table and Mollier chart. Now today we will discuss about numerical on reheat and regenerative combined vapor power cycle. So here problem is given. Help of that problem we will discuss how to obtain the efficiency of cycle. Now steam at 100 bar. So steam at 100 bar and 500 degrees Celsius expands in a turbine isentropically. So steam when enters into the turbine enters at pressure P1 of 100 bar and temperature of steam is superheated steam T sup 1 at 500 degrees Celsius expands in the turbine isentropically, means the heat transfer from system to surrounding or surrounding to system is 0 till it becomes dry saturated. Steam is expanded till it becomes dry saturated, means at point 2 after expansion the steam dryness fraction is equal to 1. So then it is taken out and reheated to original temperature. Again it is reheated to original temperature. So temperature of steam at point 3 T sup equal to 500 degrees Celsius. So temperature of steam is again raised to 500 degrees Celsius and then expanded isentropically up to condenser pressure of mixing type. To improve the performance of plant, one feed heater is used by using the steam at a pressure of 5.5 bar. So this we call as pressure P3. So the steam is expanded till it becomes dry saturated. At that point we assume that pressure is P2. So steam is expanded up to pressure P2. When it becomes dry saturated, again this steam is reheated and then afterwards again it is expanded till pressure of 5.5 bar, that is P3, and then condenser pressure again some part of steam is blended out to pass it into the uh, what you call feed heater, and rest of the steam is expanded up to zero point 0.1 bar. Neglecting pump work, here it is clearly specified, neglect pump work. Find out following. So amount of heat given in reheater. So in the previous case also we have seen the amount of heat given in reheater can also be obtained per kg of steam. Then percentage of steam extracted from heater for heater. So percentage of steam extracted for heater, then work done per kg of steam supplied from boiler. So here work done per kg of steam is to be obtained. So thermal efficiency of plant is also asked. Now coming to this steam which is at 100 bar and temperature of steam is 500 degrees Celsius enters into the turbine and this steam is expanded till it becomes dry saturated. As soon as it becomes dry saturated, then it is reheated. The steam is reheated up to point 3 and again steam is expanded isentropically unless it reaches to the pressure of 5.5 bar. So here at point 4 steam of m kg is taken out for uh, a regenerative purpose, or steam is blended to heat it in heater, and 1 minus m kg is again expanded to do work, and this steam at point 5 is condensed into the condenser at point 6. So then heat enthalpy of the steam from point 6 is raised to point 7 by mixing condenser. So, and from point 7 onwards enthalpy is added. So sensible heat is added, latent heat is added, and superheat is added. So same is shown on this HS diagram. First point 1 is marked, so where pressure is 100 bar and temperature is 500 degrees Celsius. So at 500 degrees Celsius this point 1 is marked. From point 1 vertical line is drawn up to saturation curve, and from that again reheat cycle takes place. So this pressure is to be obtained. So this is pressure P2. So pressure P1 is 100. P2 is not given, so that we have to obtain. Then 5.5 bar is pressure number 3, and this is pressure PB or back pressure we can call. Then steam is expanded from 1 to 2, so where steam becomes just dry saturated, again it is reheated, then to original temperature of 500 degrees Celsius at a pressure of 5.5 bar. Then again it is expanded up to 0.1 bar, but meanwhile at 0.4, when it reaches the pressure of 5.5 bar, m kg of steam is taken out and 1 minus m kg of steam is expanded. So this is how this cycle is to be studied. So now in this case we will find out the data given. First of all, the pressure of steam and temperature of steam at inlet is given 100 bar and 500 degrees Celsius. So pressure at point 2 is not known, but condition is known that the steam is expanded isentropically till it becomes dry saturated. So dryness fraction is known. Then steam is again reheated up to 500 degrees Celsius, and then it is expanded up to pressure of 5.5 bar from temperature of 500 degrees Celsius. Then it is expanded up to 5.5 bar and m kg of steam is taken out and 1 minus m1 kg is again expanded up to the back pressure of 0.1. The temperature of steam at 0.1 is equal to temperature of steam at 0.3. Then he is asking us to find out heat supplied Q2 to 3 in the reheater. So 2 to 3 is the amount of heat supplied in the reheater, and then percentage of mass of steam taken to feed heater. So how much of steam is taken out, mass of steam that is taken out from the turbine, then work done and reheat efficiency of reheat cycle or this plant is asked. So to find out all this, we will have a plan of solving this problem. So in this plan, first of all, heat transfer in a heater is given. So where heat is transferred in a reheater is from point 2 to 3. So H3 minus of H2 gives the heat transfer in a reheater. So enthalpy at point 2 can be obtained. So enthalpy at point 2 can be known as H2 is equal to HF2 X2 HFG2, but we know X2 value, dryness fraction of point at point 2 is 1. So but HF2 and HFG2, how to know HF2 and HFG2 is the question, because we don't know pressure P2, pressure is not known, that is the question. So now here we know that the process 1 to 2 is isentropic process. The entropy at point 1 is equal to entropy at point 2. So equating entropy at point 1 at 100 bar to entropy at pressure P2. So entropy at point pressure P2 can be determined, but pressure itself is unknown. So what to do here? Entropy at point 1 can be calculated. Entropy at point 1 can be calculated because pressure is known. So SF1, SFG1, CPS, TS1 can be taken from steam table. T sup 1 is given. So left hand side can be calculated. So on other hand, we have to find out the value of Sg. So x2 value is known. X2 is equal to 1 because it is given in the problem itself that steam becomes just dry saturated. So sum of SF plus SFG must be equal to the right hand side value whatever we get. So Sg is given in the steam table. So there are three different columns, SF, SF and SF, Sg. Sg is nothing but the entropy of dry saturated steam. So this value which we get on left hand side has to be seen in the steam table for Sg. Wherever this Sg is equal to the value of entropy on left hand side, so corresponding pressure is to be noted and that pressure can be taken as P2. Once we know P2, then we can find out enthalpy at H2. So the enthalpy at H2 is just pending because we don't know P2. So from this equation, so left hand side can be calculated and that can be compared with the Sg. Wherever the left hand value is going to be equal to Sg in the column, so that Sg, corresponding to that Sg, we can locate the pressure, and that pressure, from that pressure enthalpies can be taken and H2 can be determined. So then we can find out H3. H3 is equal to HF3 plus HFG3 plus CPS T sub 3 minus TS3. This is at pressure P2. Once we know pressure P2, then we can find out S3 also. So very important role is to find out P2. So now heat balance in feed heater. So now to find out this mass of steam which is taken out for heating in feed heater, so amount of enthalpy of this m kg of steam decreases from H4 to H7. So m into H4 minus H7 is the amount of heat given by m kg of steam to 1 minus m kg of condensate to increase its enthalpy from 0.6 to 7. So this is nothing but amount of heat given is m into H4 minus HF7. M is the amount of steam taken out, so enthalpy of this steam decreases from 0.4 to 7, so H4 minus HF7, and amount of condensate which takes heat is from 6 to 7, so mass of that one is 1 minus m kg. So 1 minus m kg is heated from enthalpy from 6 to 7, so HF7 minus HF6. So this is the amount of heat absorbed by condensate, and this is nothing but the amount of heat given by steam. So in this above equation we can find out H4. Enthalpy at 0.4 can be obtained. So enthalpy at 0.4, assuming that if this is dry saturated, its dryness fraction will be 1. If it is superheated, then this formula may not be useful. So here we have to check whether at 0.4 steam is dry saturated or superheated. Depending on that, we have to write a formula here. So this is not the final formula to find out H4. So H4 has to be obtained depending on the condition or quality of steam. Then we have to find out HF7. HF7 can be obtained corresponding to pressure 5.5 bar. HF6 can be obtained corresponding to pressure 0.1 bar. HF6 is nothing but HF value at 0.1 bar, and HF7 is the HF value corresponding to 5.5 bar. Now only H4 is remaining. So once we know H4, we can know HF7, HF7, HF6. Only unknown will be M. So from this equation we can find out mass of steam that is blended out. Then to find out entropy at 0.3, so here to know the quality of steam at 0.4, here S3 at pressure P2 has to be equated to S4 at pressure 5.5 bar, because this process 3 to 4 is isentropic process. So entropy at 0.3 is equal to entropy at 0.4. So equating this, we can find out dryness fraction X4. So if this dryness fraction X4 is less than 1 or equal to 1, then our assumption of steam is wet is correct. And if this X4 value exceeds 1, then our assumption is wrong, so steam is not wet. Then we have to change this formula for enthalpy of superheated steam, and then there we have to find out temperature of superheated steam at 0.4. Then after knowing this condition of steam, whether it is wet or superheated, so either we can find out X4 or temperature of superheated steam at 0.4. So if dryness fraction is equal to 1 or less than 1, then our assumption is correct, we can proceed. But if this X4 is greater than 1, then we have to find out temperature of superheated steam, that we will see. Then once we know H4, we can substitute in this equation. Then from this equation we can find out mass of steam. Then third part is work done per kg of steam. So where work is done, so work is done from 1 to 2. So steam is expanded from 1 to 2, so H1 minus H2, this is first work. Then 3 to 4 is also work done by 1 kg of steam, so H3 minus of H4. But from 4 to 5, only 1 minus m kg of steam is expanded. Therefore the amount of work done between 4 to 5 is 1 minus m H4 minus H5. So in this what we know is H1 is already calculated, sorry, H1 is not calculated. H2 is calculated, H3 is calculated, H4 is calculated. So H1 is not known. So to find out H1, enthalpy of steam at point 1 is obtained by HF1 plus HFG1 plus CPS T sub 1 minus T saturation 1 at pressure P1, that is 100 bar. So H1 can be known easily. To find out enthalpy at point 5, we must know dryness fraction at point 5 because steam seems to be wet at point 5. So we must know X5. So to find out X5, unless we know X5, we cannot find out H5. So here again, entropy at point 3 is equated to entropy at point 5 because it is isentropic process. So entropy at point 3 is given for superheated steam at pressure P2, that is whatever is the P2 that we have to calculate in this first step only, and S5 at 0.1 bar. So from this only unknown is going to be X5. Once we know X5, we can substitute X5 in this equation, we can get H5. Once we know H5, M, everything, then work done per kg of steam can be easily calculated. So now coming to this data, so what is written in this data table is the pressure of 100 bar, at pressure of 100 bar, so data of saturation temperature, specific volume of liquid, enthalpy of liquid, latent heat, then entropy of liquid, entropy of vaporization, that is noted down from steam table. So at again 5.5 bar also this data is taken from steam table. Already you know how to extract data. Now coming to next thing, we will start to find out the values of enthalpy at various points H2, H1, H2, H3, H4, H5, and then we will find out what you call M and heat transfer, everything. So very first our task is to find out enthalpy at point 1. Enthalpy at point 1, H1 can be given as HF1 plus of HFG1 plus of CPS T soup 1 minus of T saturation 1. So this is at pressure of P1 is equal to 100 bar. At pressure of 100 bar we can find out enthalpy at point 1. So to find out enthalpy at point 1, again coming back to the steam table, enthalpy HF1 is 1408 at 100 degrees Celsius, 1408.00 plus HFG1. HFG1 is 1319.7 plus of CPS, specific heat of steam at constant pressure, is 2.1 into temperature of superheated steam T soup. So that is given in the problem itself, 500 degrees Celsius minus saturation temperature 311.1. 311.1. So this we get as H1. So 1408.00 plus 1319.7 plus 2.1 into 100 minus, so this is 31 or 24, 3124.39 kilojoules per kg. And to find out H2, enthalpy at point 2. So now to find out enthalpy at point 2, so here condition at point 2 is dry saturated steam. Already it is given in the problem. Steam from point 1 is expanded such that it becomes dry saturated. That means dryness fraction at point 2 is 1. The enthalpy at point 2 can be written as HF2 plus of HFG2 at a pressure P2. So we don't know pressure P2. So pressure P1 is known, but P2 is not known. Now this process 1 to 2 is a isentropic process. So S1 entropy at point 1 at a pressure of P is equal to 100 bar is equal to entropy at point 2 S2 at a pressure of P2 bar that we don't know. So entropy at point 1 can be written as SF1 plus SFG1 plus of 2.1 natural log, sorry, 2.1 into CPS specific heat into natural log, sorry, zero point 0.1 means it itself is CPS natural log T soup 1 divided by T saturation 1, which is equal to entropy at point 2, that is SF2 plus SFG2. So this summation of SF2 plus SFG2 is directly known as SG2 because it is dry saturated steam. So SG2 at pressure of P2. So SF1 can be taken from steam table. The SF1 at pressure of 100 bar. The SF1 at 100 bar is 3.3595. 0.3595 plus of SFG1. SFG1 is 2.2590. 2.2590 plus of CPS is 2.1 natural log T soup 500 degrees Celsius plus of 273 divided by saturation temperature at this pressure of 100 bar. Saturation temperature at 100 bar is 311.1. 311.1 plus of 273. So this must be equal to ESG2 at pressure P2. So left hand side we can calculate 3.3595 plus of 2.590 plus of 2.1 into natural log 500 plus 2 plus 2. Left hand side becomes 6.20. This becomes 6.06 kilojoules per kg Kelvin. On right hand side SG2 at pressure P. So this is to be seen from steam table. So in steam table, if we see this value of SG, so there will be a column. Entropy column is divided into three parts. One is SF, then another is SFG, and third one is SG. So we have to search in this column for this value of 6.20. So for value of 6.20, if we search 0.20 corresponding to 6.20, pressure is 28.5 bar. So what we have to do is we have to search for 6.206 in the steam table in the column of SG. In the column of SG, wherever we get value of 6.206 for SG, so there are three columns, so 1, 2 and 3. So generally we copy this data from steam table, so this data we are not going to copy. So in this column we have to search for this value of 6.206. 6.206 corresponding to that pressure is 28.5 bar. So here we can write down pressure P2 is equal to 28.50 bar corresponding to SG is equal to 6.206 kilojoules per kg Kelvin. So this is we have to see in this column wherever we get this value of 6.206, corresponding to that on this side there will be pressure. So this pressure has to be noted wherever we get this value. Say for example, this is pressure column, and this is SF column, then this is SFG column, then SG column. So again here HF, HFG, everything will be there. Wherever we get this 6.206 corresponding to that, this pressure has to be seen, and this pressure is 28.50 bar. So now we know P2 as 28.05 bar. So corresponding to 28.5 bar, we can collect this data here. So this pressure is known to now 28.5 bar. So corresponding to 28.5 bar, so saturation temperature is 231.00 degrees Celsius. Specific volume of liquid is 0.00111, and corresponding to that HF value is 995, 995.00. Then HFG value is 1807, 1807.00. SF value is 2.61, 2.195. SFG value is 3.5841, 3.5841. And after this there will be column of SG where we have compared this value. So summation of SF plus SFG is nothing but SG column. This data is taken from steam table. So now coming back to point 2, once we know pressure at point 2, we can find out enthalpy at point 2. H2 is equal to HF2 plus HFG2, dryness fraction value is 1. HF2 already just now we have copied as 995 plus of HFG2 is 1807. 1807. This will be the enthalpy at point 2. 995 plus 1807 gives us 802. 802 kilojoules per kg. So now we know H1, we know H2. H1 and H2 values are known. So now coming to H3, so enthalpy at point 3 can be obtained because we know pressure. Enthalpy at point 3, H3 is equal to condition of steam at point 3. If we see, it is a superheated steam. So we have to write formula for superheated steam. HF3 plus of HFG3 of PS 3 minus T saturation at point 3. So this is at a pressure of P2 equal to 28.5 bar, just we have obtained. Now we know pressure P2. So HF3 can be taken at pressure P2. At pressure P2, HF3 is 995 and 1807. 993 plus 1807, 995. 995 plus 1807 plus CPS is 2.1. Temperature of superheated steam is 500 degrees Celsius minus saturation temperature at pressure of 28.5 bar from steam table is 231. Saturation temperature is 231. So here we can write 231. From this we get H3. The H3 value we will write here as 995 plus 1807 plus 2.1 into 500 plus 31. So this is 3366. 0.9 kilojoules per kg. So now we know enthalpy at point. So to find out enthalpy at point 4, H4. So just we assume that enthalpy at point 4 can be obtained as HF4 plus X4 FG4. Assuming, what is assumption? Assuming that steam is wet and steam is expanded from point 3 to 4. This point 4 is assumed inside, and with the assumption that steam is wet, we have written this formula. If steam is superheated, we would have written some different formula, that is HF4 plus HFG4 plus of CPS T sub 4 minus T saturation 4. So here to find out enthalpy, either we need X4 or we need T sub 4. So at pressure of, this is all data is at pressure of P is equal to 5.5 bar, because pressure at point 4 is 5.5 bar. So now to know dryness fraction, so presently we are assuming that it is wet steam. So to know dryness fraction at point 4, first we have to equate entropy at point 3, that is at pressure of P is equal to 28.5 bar, that is equal to entropy at point 4 S4 at pressure of P is equal to 5.5 bar. So this is at 5.5 bar, this is at pressure of 28.5 bar. So condition of steam at point 3 is superheated. So here SF3 plus of SFG3 plus of CPS natural log T sup 3 divided by PS, the saturation temperature at point 3, which is equal to entropy at point 4. Entropy at point 4, what we have assumed is at point 4 steam is wet. So SF4 plus of X4 and SFG4. So this is taken at pressure of 5.5 bar. This is taken at pressure of 28.5 bar. So we will take the values of SF3 and SFG3 from steam table at 28.5 bar. So at 28.5 bar, this is 2.6195, 2.6195, 2.6195 plus of SF3 at 28.5 bar. This is 3.5841, 3.5841, 3.5841. So S3, SFG3. PS is 2.1. Natural log temperature of superheated steam. So at point 3, steam is at temperature of 500 degrees Celsius. So 500 degrees Celsius plus 273, always this must be in degree Kelvin, divided by saturation temperature at 28.5 bar. So saturation temperature is 231 at pressure of 28.5 bar, 231 plus of 273, which is equal to S4, SF4 at pressure of 5.5 bar. At pressure of 5.5 bar, it is 1.8912, 1.8912 plus of X4 into SFG4. SFG4 is 4.892, 4.892, 4.82. So if this dryness fraction value we get equal to 1 or less than 1, then our assumption which we have made here is correct. What is the assumption? Steam at point 4 is wet. So if this dryness fraction X4 is equal to less than 1 or equal to 1, then this assumption is correct. If this is greater than 1, then our assumption is wrong. Then these steps have to be repeated once again. So now we will see what will be the value of dryness fraction in this case. 2.6195 plus of 3.5841 plus 2.1 into natural log 500 plus 273 divided by 31 plus 273 minus 1.8912 divided by 4.892. So dryness fraction x4 we are getting as 1.06. That means always it is to be remembered that dryness fraction is less than 1. So this indicates this assumption is wrong. Therefore, we have to switch to this next formula to find out enthalpy, and this formula to find out entropy is also wrong because it is indicating that steam at point 4 is superheated, not a dry saturated. So again, coming back to here, so entropy at point 3 is equal to entropy at point 4. So here we write SF3 plus of SF3 plus of CPS natural log T soup divided by TS 3 is equal to SF4 plus of SFG4 plus of CPS natural log T soup 4. Please assume that now the steam is superheated at point 4, so we are writing this formula, and T saturation 4. So here left hand side will be same as it is, 2.6195 plus of 3.5841 plus of CPS is 2.1 in natural log 3, so 500 plus 273 770 divided by, so this will be 400 500 504 504 200 200 400 470 plus 30 500 504 504, which is equal to SF4. Again SF4 value is 1.8912 plus SFG4 is 4.892 plus of CPS is 2.1 natural log T sub 4 we don't know, T sub 4 we have to find out, and denominator S4 TS4 saturation temperature at point 4 is known to us. Saturation temperature at 0.5 bar taken 5.5 bar, it is 155.48 so 155.48 plus 73. So from this we can get temperature of superheated steam T sub 4. So once we know T sub 4, we can find out enthalpy at point 4. So to find out this, we'll see 2.6195 plus 0.5841 plus 2.1 into natural log 770 divided by 504 minus 1.891 to 1.8912 minus 4.892 divided by 2.1, 0.17, 0.1575. So this T soup 4 is 498.66 Kelvin. So this will be in Kelvin. So minus 273, 225.66 degrees Celsius. So temperature of superheated steam is known at zero point 0.4. Enthalpy at zero point 0.4 H4 can be obtained as HF4 plus HFG4 plus of CPS T soup 4 minus T saturation 4 at a pressure of 5.5 bar. At pressure of 5.5 bar, HF4 can be taken from steam table. So HF4 at 5.5 bar is 655.91. 655.91 plus of HFG4. HFG4 is 20.96.04. 20.96.04. 20 point, it is 2096.04. 2696.04. The specific heat is 2.1. Temperature of superheated steam is 225 degrees Celsius. So both we will substitute in degree Celsius. 225.66 minus saturation temperature at pressure 4 at pressure 5.5 bar is 155.48. 155.48. 155.48. On simplification we get H4 as 1 4 plus the enthalpy H4 is equal to 899.34 kilojoules per kg. The H4 is known. Now H5 has to be obtained. So to find out H5, again H5 again we assume that is wet. HF5 plus of X5 into HFG5, assuming steam to be wet at 0.5. The steam is assumed to be wet. So X5 dryness fraction is not known. So to find out dryness fraction, we again equate entropy at 0.3. So at pressure T2 is equal to 28.5 bar. Entropy at 0.3 is equated to entropy at 0.5, that is just 5. At pressure of PB is equal to zero point 0.1. Here now we assume at 0.5 steam is wet and at 0.3 steam is superheated. So SF3 plus of SFP3 plus of CPS natural log T soup 3 divided by TS is equal to SF5 plus of X5 SFG 5. So this right hand side is at pressure of 0.1 bar, on left hand side is at pressure of 28.5 bar. So these values are taken. S3 again 2691, SF3 is 269, 2.6195, 2.6195, 2.6195 plus of SF3 3.5841, 3.5841 plus of CPS is 2.1, natural log P soup is 773 divided by 704, 773 divided by 504 equal to SF5 at a pressure of 0.1 bar. So coming back to the steam table, data has to be taken at steam table. 0.6492 at pressure of 0.1 bar. So 0.6492, 0.6492 plus of X5 into SFG5 at pressure of 0.1 bar from steam table. 7.5010, 7.5010, 7.5010. So here we can find out X5 dryness fraction. Again, if this dryness fraction is equal to 1 or less than 1, our assumption which we have made here is correct. If it is greater than 1, then assumption is wrong, and we have to find out temperature of superheated steam. 2.6195 plus of 3.5841 plus of 2.1 into log 773 divided by 504 minus 0.492 divided by 5. Dryness fraction we get as 0.86, means our assumption is correct. So with this we can find out enthalpy at 0.5. H5 is equal to HF5 plus of X5 into HF5. HF5 is taken from steam table at pressure of 1 bar, 0.1 bar, 191.81, 191.81, 191.81 plus of X5 is 0.86 into HFG5. FG5 value is 2392.82, 2392.82, 2392.8, 392.8, 39.82. So here we get H5 as 191.81 plus 0.86 into 392.82. So this is 2249.3 kilojoules 22.49.63 kilojoules per kg H5 is known. Now from steam table we can find out H6 is nothing but HF6, pressure of 0.1 bar. So at pressure of 0.1 bar, HF5, so this HF5 value is 191, HF5 and HF6 will be same. So here this will be 191.81 kilojoules per kg, and then H7, enthalpy at 0.7 is HF7, So it is at pressure of 5.5 bar. At 5.5 bar, so HF4, HF7 is equal to HF4. HF4 we can take from steam table, and that is pressure of 5.5 bar. HF4 is, you can see here, 655.91, 655.91. So once we will summarize this data, and then we can find out the things which are asked in this problem. So now first one we write H1 value, H1, then we write H2 value, then we write H3, we write H4, then we'll write H5, then H6, then H7. So these values we take from this solution. H1 is 3124.39, 3124.39, 3124.39 kilojoules per kg, and H2 value which we have obtained is 2802, 2802 kilojoules per kg. Then H3 value which we have obtained is 3366.9, 3366.9 kilojoules per kg. In H4 value is 2899.34, 2899.34 kilojoules per kg. And H5 value which we obtained here is 2249.63, 2249.63 kilojoules per kg. H6 is 191.81, 191.81 kilojoules per kg. Then H7 is 655.91 kilojoules per kg, 655.91, 655.91 kilojoules per kg. So now this is about the data which we have collected. Now we can find out the information which is asked in this problem. So what is asked in this problem, that we see once again. So he has asked us to find out heat supplied in a heater, the mass of steam taken out, and then work done and efficiency of cycle. So here to find out this heat transfer in a reheater, so this is Q2 to 3, heat supplied from 2 to 3 can be obtained by H3 minus H2. So first we will find out heat supplied in reheater Q2 to 3, which is equal to H3 minus H2. H3 value is known, that is 3366.9 minus H2 is 2802, which is equal to 3366.9 minus 2802. This is 564.9 kilojoules per kg. The heat supplied is known now. So this was heat supplied. Then mass of steam taken to feed heater. So here we have an equation, m H4 minus HF7 is the amount of heat given by steam, and this is the amount of heat taken by steam. From this we can find out mass of steam taken out. So percentage is asked here. So here we write this, mass of steam m kg is taken out. So that gives enthalpy from H4 to H7 reduces, and amount of heat is gained by 1 minus m kg. So that is increasing enthalpy from 6 to 7, H7 minus H6. So here m kg of steam gives its heat to reduce its enthalpy from 4 to 7. So H4 minus H7, m into H4 minus H7 is amount of heat given, and 1 minus m kg of condensate is using heat to increase its enthalpy from 6 to 7. So H7 minus H6, 1 minus m. So m is taken as it is. H4 value we know as 2899 minus 2899.34 minus H7 value is 655.91, which is equal to 1 minus m. M is unknown into H7. H7 is 655.91 minus H6 is 191.81. On simplification we get the value of m here. So the value of m can be obtained, m into, so this term 2899.34 minus 655.91. So this is 2243.43, which is equal to, so this we simplify, 55.91 minus 191.81 multiplied by 1 means this is 464.1 minus of 464 m. So m terms we collect on one side. So here m into, so this plus this plus of 2243.43, this is 2707.53, which is equal to 464.1. So m is equal to 0.17. So that is nothing but in percentage out of 1 kg. So this much of 0.1714 kg of steam is blended out. So in percentage, if we find out, the percentage of mass of steam taken out is 17.14. 17.14% of steam is taken out or blended out. Then after that, what he is asking is 0.1 divided by 2707.53. Okay, this is correct. 17.14% of steam is taken out in this feed heater or heater, mixing type of heater. Then he is asking us to find out efficiency. So this is obtained, then work done and reheat cycle, efficiency of reheat cycle. So net work done we can find out, net work done or work done is equal to work done by the turbine minus pump work is neglected. So here work done is given by H1 minus H2. So first work done is W1 from 1 to 2, and second work done is from 3 to 4. So 1 to 2 plus H3 minus H4 plus 1 minus M H4 minus H5. H1 value we know 3124.39, 3124.49 minus H2 value is known 2802, then plus of H3 value we know 3366.9, 3366.9 minus H4 value is known 2899.34, 2899.34 plus 1 minus m, 1 minus m, minus m means 0.1714, just we have calculated 0.1714 into H4 value is 2899, for value is 2899.34, 2899.34 minus H5 value is 2249.63, 2249.63. So here net work done, we can call this as a net work done, can be obtained. So net work done will be 3124.49 minus 2802 plus 3366.9 minus 2899.34 plus 1 minus 0.1714 into 2899.34 minus 2249.63. This is 1328, 1328.39 kilojoules per kg. So this is net work done. Then heat supplied has to be obtained. So to find out efficiency, heat supplied is to be calculated. So where heat is supplied, the heat is supplied from point 7 onwards, point 7 to 1. So H1 minus H7. So this is one part of heat supplied from 7 to 8, 8 to 9, 9 to 1. This is first heat supplied. Then heat is supplied in reheater from 2 to 3. So H3 minus H2 plus of H3 minus H2. So this is again heat supplied. So here this heat was not considered in previous problem. So actually this heat has to be considered in finding net heat supplied. So in a reheater heat is supplied here. So this heat is considered, but this heat is not considered from 6 to 7 because this is exchange of heat. So actually this amount of heat from 7 to 8, 8 to 9, 9 to 1 is supplied, as well as a heat from 2 to 3 is supplied. So net heat supplied, H1 value is known, that is 3124.49 minus HF7 or H7. H7 value is 655.91, 655.91, 655.91 plus of H3 value is 3363, sorry, 3366.9 minus of H2 value is 2802. 2802. So you can see here H2 value. H2 value is 2802. So from this we can get heat supplied 3124.49 minus 655.91 plus 3366.9 minus 2802. So this will be 30.33, sorry, 33.48 kilojoules per kg. So Rankine efficiency or efficiency of this cycle is given by net work done divided by heat supplied into 100. So there was a mistake in previous problem that directly we have added heat supplied in the boiler, but this heat supplied in reheater was not considered in the denominator. Please make the correction in previous problem. So here net work done is 1328.39 divided by heat supplied is 3033.48 into 100. So this gives us 1328.39 divided by 33.48. The efficiency will be 43.79%. Here efficiency is obtained. So these are the things which are asked in this problem. So coming back to the problem, what is asked in this problem? Work done is obtained, reheat cycle efficiency is obtained, heat supplied in reheater, and mass of steam that is taken in the filter. All four things are obtained here. So this is how a problem using steam table can be solved, and the data or the answers can be obtained. So here mass of steam is 17.414%. So summary can be written here. So mass of steam blended out M is equal to 17.14%. Then heat transfer Q2 to 3 or in reheater is equal to, so Q was 564.9 kilojoules per kg. Then work done, which is equal to 1328.39 kilojoules per kg, and efficiency is equal to 43.79%. So these are the answers which we have obtained from using steam table. So just we will have a review and how to use the Muller chart to find out various enthalpies and how to plot this problem on Muller chart. So here very first what is given is pressure P1 is equal to 100 bar. So 100 bar line is traced, and wherever it intersects with the temperature line of 500 degrees Celsius, that point is marked. So from this point 1, the vertical line is traced, and wherever it intersects with saturation curve, that point is selected, and from this here pressure is obtained P. The pressure can be seen here, P2 is obtained, and from that point again this is what we say is traced up to point 3. So at constant pressure P2, so this temperature of 500 degrees Celsius, wherever it intersects, that point can be taken, and from point 4 or 3 the vertical straight line is taken up to point 1 bar. So in between this intersects with the pressure line of 5.5 bar. So this is seen with the help of the graph which I have shown here. So you can find the pressure line of 100 bar which intersects with the temperature line of 500 degrees Celsius at point 1. So corresponding to point 1 we can find out enthalpy as 3360. So in previous case enthalpy was 3360, here it is 3124. So here this is nothing but the error, graphical error. So from this a vertical line is taken, and wherever it becomes dry saturated, that point is 2. So corresponding to point 2, enthalpy is taken here as 2775. 2775 is the enthalpy. So here in graphical analytical method 2802. So there will be a difference, error will be there. And again, from at this point, whatever is the pressure, along this pressure, this line is traced, and where it intersects with again 500 degrees Celsius, that point is to be located. And at that point, point 3 is taken, and from point 3 if we see, the enthalpy will be 3485. So H3 is 3485. H3 is 3485. So here 3366. Then again from that point, vertical line is traced up to the pressure of zero point 0.1 bar. So meanwhile, so this intersects with the pressure line of 5.5 bar. So here there is pressure line of 6 bar, and here there is a pressure line of 5 bar. So 5.5 bar is not available. So we have to take one line between this, in between these two lines, and point is marked. So enthalpy at point 4 is taken as 3275. 3275 is enthalpy at point 4. So enthalpy at point 4 is 3275. So approximately values will vary. So approximate values we get by using Molière chart. Then this point 3 is projected up to point 5, where it meets with the pressure line of 0.1 bar, and corresponding pressure enthalpy is taken at H5 is 2455. 2455 is enthalpy at 0.5. 2455. 2455, here it is 2249. So there is a difference. By using this Molière chart, we can find out certain values, but those values will not be more accurate. There will be error. So erroneous values will be available. Better to practice solving these problems using uh, steam table rather than Molière chart. So the accuracy will be less and time consumption will be more. So in case of steam table, the accuracy will be more and time consumption will be more, whereas in graphical method, time consumption is less and accuracy is also less. So it is up to you to decide whether to use Molière chart or to use steam tables to simplify. So in case of steam tables, you need to remember so many formulae to find out H1, H2, H3, H4, but whereas in Molière chart, you need not to remember so many formulas. Find out this what you call. So here one more thing you can find out in this Molière chart, dryness fraction. Dryness fraction is 0.94. So at 0.5 dryness fraction is, we can find at x5. X5 was 0.86. There was 0.95. So such errors will occur in graphical method. Better I suggest to go for analytical method. In case if you are having shortage of time, then you go for Molière chart. So I hope you have followed these methods to solve problem on a reheat cycle and regenerative cycle. So please do the correction in previous problem, in previous lecture, while finding heat supplied. So I had considered only heat supplied from boiler from 0.7 to 1 say. I had not considered the heat supplied in this reheater from 2 to 3. So please consider that heat, and then recalculate the efficiency of a previous problem, not of this problem. This problem is correct, no problem, there is no doubt. But in the case of previous problem or previous lecture, so efficiency was calculated based on heat supplied. So the calculation of heat supplied, whether it includes complete heat supplied or only the heat supplied in boiler, it has to be seen. So amount of heat supplied in boiler is different and amount of heat supplied in reheater. Both heats have to be considered in the amount of heat supplied. So here I have considered, but in previous problem I had left this second part which was not included. If it was included, well and good. If it is not included, please do recalculations for only heat supplied and efficiency. Thank you.